Hello everyone, it's Mr. T again and welcome back to physics. This week we are going to be talking about free fall. So hopefully by the end of this video you'll be able to answer what is the meaning of free fall and under what conditions does it occur? What excuse me. What is the value for the acceleration of gravity, also known as g? And how do you calculate how fast and how far a free falling object will move in a given amount of time? So let me get my pen here ready and let's move on. So free fall. What would we consider an object in free fall? Well, if you're anything like me, you get a question like that and you're like, I don't know, let me Google it. So let's Google it. When you do that, you're going to get an answer that looks like this. The textbook definition, which says an object is in free fall when the only force acting on it is the force of gravity. Okay, well, that's well and good, but what on earth does that mean? Because I can tell you what we haven't covered in physics yet. So your first question should be, what is a force? Because we kind of know what that is, but we haven't really talked about what exactly technically it is. What's a force? And what's the force of gravity? So this force of gravity. What are those? So if we take those out, an object is in free fall when the only thing we don't know acting on it is the also thing we don't know. Not particularly helpful. Not helpful. Thanks, Google. You're not helpful. And this is why I say it's always important to put notes in your words and don't just copy things down, because if you copied this down, you would have no idea what it means. This doesn't actually answer the EQs. But we can answer it in a way we do understand. So, Spider-Man. I like Spider-Man. You like Spider-Man. Everybody likes Spider-Man. If Spider-Man were to jump off a skyscraper. So we got a skyscraper with all the little windows down. You know what? Not jump. Let's say he just kind of falls off. He launches himself off, right? Before he launches a web to attach himself to another building. So Spider Man's falling. We would probably consider him to be in free fall. That seems fair, right? That's a general idea. When we hear that word free fall, to fall freely, that's what we think of. So, what does that mean in a better way we can understand? Well, one, can't be touching any other objects. When Spider-Man's falling, he's not touching anything. Okay, that's why I said it's before he shoots the webs out of his little web holders, or if you're in the Ultimate Universe, out of his hands. So before he shoots the web, because then he'd be touching something, right? He'd be touching the web, touching the building. So while he's falling, he can't be touching any other objects. And two, that object technically includes air. So there is a thing called air resistance. If you've ever been falling yourself, you know you can feel the air pushing back on you like wind. So, Spider Man, technically, to be in free fall, would have to be in a vacuum. When you see the word vacuum, that just means without air. That's why we call the machine that picks up dirt on the carpet a vacuum, because inside of it, there's no air. And that's what sucks things in. We will talk about that a little bit later in the year, why things move from areas where there's a lot of something to areas where there's not a lot of something. You'll also learn about that in chemistry. That's just a fact of existence. So there can't be air either, technically. So here's rule number 3. We lie. So we all know there's air on planet Earth, right? Well, we're going to pretend there's no air for these problems to make our life a lot easier, okay? We're going to pretend there's no air. Honestly, air resistance, if you can do the calculus to figure out what it's like with air resistance, it's negligible most of the time, because the objects we're calculating are either so small that air resistance doesn't matter, or they're so big that air resistance doesn't matter. But so we're just going to pretend for all intents and purposes there's no air. Okay, so to be in free fall, where it actually makes sense, unlike the Google definition. Can't be touching other objects, no air resistance. We're going to lie and pretend there's no air in these situations because honestly it makes the math 100 times harder, but the difference it may make in an answer is the difference between 1 and 1.0001, which gets rounded off anyway. Other things to know when we're talking about free fall. So when you're in free fall, gravity is always pulling you down, right? That's something we can feel. When gravity's pulling you down on planet Earth, oh geez, look at me, lowercase. On planet Earth, it's pulling you downward at 9.81 meters per second squared. That's an acceleration. It's acceleration, like it says. Okay. Another way you can write this is negative 9.81 meters per second squared. So 9.81 meters per second squared downward and negative 9.81 meters per second squared, those are the same thing. Those are two different ways to write the same thing. This is also known as G for gravity. Okay, so you can write it more often than not in a math problem. You're going to use the one with a negative because it's kind of hard to keep track of the word downward in the middle of an algebra problem. 2, another thing we need to know. Objects being dropped have an initial velocity of 0 meters per second. That makes sense. Again, if we go back to Spider-Man on the building, and he doesn't jump in the air, but he just kind of falls off the building to do a superhero landing. His initial velocity is 0. Then as gravity pulls him down, he's going to speed up, and he's going to keep speeding up. Okay, that's what gravity does. It accelerates you from 0. So keep in mind, objects being dropped have an initial velocity of 0 meters per second. 3, the other thing to keep in mind is mass doesn't matter. It doesn't matter if Spider-Man weighed 500 kilograms, if he weighed 1,000 kilograms, if he weighed 2,000 kilograms. It doesn't matter. Gravity is going to pull down on everything equally. I know that seems a little weird. I'm going to have a demo in class to show you. Even with air resistance, obviously our classroom's going to have air resistance. We don't exist in math problem land where we can just lie and pretend there's not air resistance. It really doesn't make that much of a difference. So how do we know it doesn't make that much of a difference? Well, when we look at our math, look, our new math. When we look at our math, there's no mass anywhere in here. So if you're in my pre-AP physics class, you've already seen these problems. Yay. If you're in just a good old-fashioned physics class, on-level physics, these are new to you. Don't freak out. These are 4, though, very important equations. Okay? Technically, they all come from one big equation, but I'm not going to spend the 30 minutes to show you how these all come from one big equation because it would honestly take me 30 minutes to derive this. If you really want to know, stay after school one day and I'll show you, but I'm not going to waste a video about it. What you need to know is that these equations do work, they do make sense, and they did help us calculate. That's how we know. These formulas are how we know what gravity is on Earth and other planets for that matter. So if we look at this one, you have displacement is equal to the initial velocity of an object times time plus 1/2 times the acceleration of it times time squared. You have this one, final velocity squared is equal to initial velocity squared plus 2 times the acceleration times displacement. Keep in mind, these are displacement, not distance, so they do care about direction. And then you got these guys on the bottom. I won't go through, it's all the same variables, okay? You don't need to memorize these. I'm always going to have these on the board. They're always going to be in the red folders available to you. It's just important to know how to manipulate these so you can solve for different variables in class, okay? So free fall again, on Earth, 9.81 meters per second squared downward, or negative 9.81 meters per second squared. Objects being dropped have an initial velocity of 0. Mass doesn't matter. As you can see, it doesn't matter. There's not mass in any one of these. Mass has nothing to do with it, as odd as that may seem. So let's try a practice problem. Mr. T drops a basketball from 2 meters in the air. What is the velocity of the basketball right before it hits the ground? So take a minute, see if you can solve this on your own. Use the equations up here. Use these. Pick one. Use guess and see if you can solve. All right, so hopefully you paused the video. You're coming back now. You gave it a try to see what you got. I'm going to give it a try too. And you're going to see probably a very common mistake everybody makes that may be confusing. So let's start with guess. RG, what are we given? Well, 2.0 meters. That's the only number I see, right? And that would be, it's meters. So that's our displacement. That's D. What on earth else do we have? That's all it gave us, right? Well, if we go back and we look, there are some other things we know. Objects being dropped have an initial velocity of 0, and we know our acceleration on Earth. We're going to assume this problem is on Earth. So we know v sub I, initial velocity, is equal to 0 meters per second. And we also know what A is. And A in this instance is going to be 9.81 meters per second squared downward, or because we're in a math problem, I'm going to write it as negative 9.81 meters per second squared. So we have three things now. We can make these problems work. What are we looking for? Well, we're looking for the velocity of a basketball right before it hits the ground. And it's important to understand when we're looking for a velocity right before it hits the ground, that's still final velocity. Why is that the final velocity? Well, because we said in free fall, it's only in free fall when it's not touching anything. So the second that basketball hits the ground, it's touching the ground now. So it's not in free fall anymore. So that velocity of 0 once it hits the ground doesn't count, not in free fall. So the actual final velocity for free fall is right before it hits the ground. So we have our variables. What equation are we going to use? Let's see. We have displacement equals initial velocity. Good. Times time. Not so good. We don't have a time. So right out. Final velocity equals initial velocity plus acceleration time. Nope. Time again. Bummer. Can't use that one. Final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. Winner, winner, chicken dinner. We have all those. So let's write that down. Final velocity squared is equal to initial velocity squared plus 2 times acceleration times displacement. There's our equation. So let's substitute. So we have final velocity squared, initial velocity squared, hey, 0, perfect, 0 squared, plus 2 times negative 9.81 times 2.0. Okay, so let's bust out the calculator. That 0 just goes away, thank goodness. 2 times negative 9.81 times 2 again would be negative 30, what is it, 39.24. All right, so now we're running into a problem. So we have VF squared over here. So to solve it, we should take the square root of it. The only issue is we're now taking the square root of a negative number. And for those who remember from algebra class, you can't take the square root of a negative number. If you try to punch this into your calculator right now, square root of negative 39.24, it's going to give you an error basically, or it's going to say invalid number. It's going to say imaginary number. If you've heard of those, it's not a real number. You can't, because you can't take two of the same number, multiply them together, and get a negative number. Because if you take negative 2 times negative 2, you get 4. You don't get negative 4. It's impossible. So that means we messed up somewhere. Yay! No, this is okay. I always leave in mistakes so that way you can see, because these are very common mistakes, like I said at the beginning. So where did we mess up? Take a minute, pause the video, see if you can find where Mr. T messed up. I'll give you a clue. It's not an arithmetic error. It's not me multiplying numbers incorrectly. It is a conceptual error. So take a minute, pause, and come back. All right, welcome back. Hopefully you've found the error. I will tell you the error is the displacement. Okay, so I said the displacement was 2 meters. That's incorrect. The displacement is not 2 meters because if you remember, this is displacement, not distance. Displacement cares about direction. So this displacement is 2 meters downward. And like I said with gravity, what's another way to write something downward? You put a negative in front of it. So it's not 2 meters. It's negative 2.0 meters. And then you make this number a negative times a negative is a positive. So you'd get positive 39.24. Good. So then you can take the square root of that and you get final velocity is equal to 6.26418, etc., etc., etc. Round it for sig figs, 6.3 meters per second. So the velocity of the basketball right before it hits the ground is 6.3 meters per second. Okay, I left that mistake in because I wanted you all to see how simple it can be to make that mistake. My saying on this is you have to be smarter than your calculator. You can't just throw numbers in there. You have to realize what direction things are moving, and you have to think about the problem. Okay, another common mistake you'll get in problems is people come up with an answer with a negative time. Like your answer could be like t equals negative 3.1 seconds. That doesn't make sense. You can't have a negative time. We haven't figured out how to travel back in time yet. You can have a negative displacement, you can have a negative velocity, we can move backwards, but you can't move backwards in time. So these are things you have to think about. Your calculator might spit out an answer like this, and you have to look at yourself and realize, wait a minute, negative time, that doesn't make sense. Okay, part of physics is being able to look at a problem and realize when it doesn't make sense. If we're talking about a problem with a person on a bicycle and your answer comes out to the person on the bicycle is moving 10,000 miles per hour, there's probably a mistake somewhere over here in the math. So this was a good example. These are equations. Like I said, don't memorize these, but get used to using them, because we use these when we talk about momentum. We use these when we talk about projectile motion. We use these when we talk about circular motion and a whole bunch of other stuff. Everything that moves uses these equations. So last but not least, what did we get today? Well, what's free fall? Free fall involves objects that have nothing touching them. Free fall, including the ground and air. Check mark 1. The acceleration on Earth, also known as g, is equal to 9.81 meters per second squared downward, or negative 9.81 meters per second squared. And remember, that's just for Earth. If you were on the moon, for example, the moon would be 1.62 meters per second squared on the moon. It changes depending on where you are. So let's say that's G moon. So this is just for Earth, but almost all our problems are going to be involving the Earth. So check 2, we got that. 3, these kinematic equations can be used to calculate how fast and how far objects in free fall move. So we are going to be using these equations quite a bit. People in engineering degrees, architecture, use these all the time too. It's useful anytime you want to calculate how fast something goes, how far something goes, the time it takes something to move. So that should cover all of our EQs. Thanks for watching. Hopefully this was helpful to y'all, and see you in class.